Good afternoon or evening. We are going to get into our new and next chapter looking at electrons. As it says here, don't write it. I'm going to give you a few seconds to read this on your own. All right, just a little thing by Richard Feynman. Again, those of you that watch The Big Bang Theory, they make reference to Richard Feynman a lot. All right, so we kind of saw this before, the Bohr model of the atom, when we talked about the structure of the atom. Bohr, again, was the student of Ernest Rutherford, and he pictured the electrons orbiting the nucleus, like the planets orbiting the sun. So he called it the planetary model. Yes, as I had said before, it was wrong. It turned out to be, more like bees around a beehive, especially when you anger the bees by playing with the hive. But that's kind of the idea of what the electrons are actually doing. So our quantum mechanical view of the model is our modern take of the structure of the atom, but also takes into account what the electrons are doing, how they are doing it, and also can answer a little bit of why they are doing what they are doing within an atom. So they use math. We're not going to get into this lovely calculus stuff that actually talks about it, but they use math laws to identify regions of space in the electron cloud. So electrons hang out actually in certain areas of an atom. Can they go anywhere in the electron cloud? Of course they can, except they cannot go inside the nucleus. They can get close to the nucleus, they can get further away from the nucleus, but they cannot go into the nucleus. And interestingly, the electrons tend to stay home, if you will. There's certain regions of space that there is a higher probability of finding those electrons. And yes, the math, again, calculus, even above calculus. So we're not going to get into the math. Don't worry about the math. When you get to college, then you can play with the math. So what these mathematical functions predict is atomic orbitals, a mathematical representation of space. So it's basically an area where an electron is most likely to be found, or a probability cloud. So obviously it's not guaranteed, but it's of high probability. Approximately, these mathematical functions which support the atomic orbitals represent a 90% probability. So it's a pretty good chance, but again, not a guarantee. So again, kind of saying the exact same thing. It's just a region in three-dimensional space where you have a high probability of finding an electron. It's a mathematical function, crazy math. So again, don't worry about the math. These shapes we're going to look at that are defined by these mathematical functions, as I said, 90% of the total electron probability. So there's still 10% out there where electrons can exist at any given moment. But for the most part, they're going to hang out in these certain shapes that we're going to get into. Any questions so far? Next. All right, so if we look at a hydrogen atom, we know it has the nucleus and it has one electron. And as you can see from this diagram, the brighter blue, or the more intense blue, is the higher probability of where the electron is going to be found. Now, clearly we can see that the electron is all over the place. But right here, closest to the nucleus, is where the electron spends most of its time. But realize it can go anywhere within this atom. So how do we describe these orbitals? I kind of already gone into it a little bit. We'll go a little further. Energy levels to start. The orbitals, these mathematical functions, are within energy levels. Now, each energy level is basically a period or a row on the periodic table. Whereas the first row, looking at a periodic table, starts with hydrogen. As we go down the periodic table, we are adding successive energy levels, 1 to 2 to 3 to 7 currently. Could there be more? Who knows? We'll see within time. Then we have these shape. The orbitals have shapes. Now, these atomic orbitals exist within an energy level. So energy level 1 has its orbitals, energy level 2 has its orbitals, and so forth. Are all orbitals that we're going to see, are they all in each energy level? No, they are not. And as we go through the electron chapter, as we get into the periodic table, we'll see that these orbitals do not all exist in every single energy level. Orientation. So again, we are talking a three-dimensional shape. Atoms are three-dimensional. Yes, we represent them with a sphere, but atoms are not actually spherical. They do not have an edge. There is no perimeter. There is no fence to keep electrons inside. It doesn't actually exist. But we can describe a shape based on our 3 dimensions of space. Also, we need to look at how many electrons can exist in each orbital. And when I talk about each orbital, I'm talking about a singular orbital, which will make sense in a little bit. So we did talk about different energy levels. You guys probably, when you used to draw an atom, you used to draw these rings, or you called them shells. N equals 1, 2, 3, 4, and so forth. Notice that each ring is larger than the next one before it. So on the periodic table, N equals 1. N, lowercase n, is the letter we use to denote energy levels. Energy level 1 is the row of hydrogen and helium. Energy level 2 starts with lithium. Energy level 3 starts with sodium, and so forth. So as you go down the periodic table, the energy levels are getting larger and larger, which, yes, that means the orbitals themselves are getting larger and larger. So again, 1 through 7, there's a period there because currently there are only 7 periods or 7 rows on the periodic table. Theoretically, if we get to element 119, that would be N equals 8, if we ever get there. 1 is the lowest, closest to the nucleus, and so forth. So, of our atomic orbitals, remember, orbitals also called sublevels. Your energy level is your big ring we just saw. Your sublevels exist within the ring. We have SPDF. Yes, they're literally called SPDF. The shapes have these funny names, but again, they're just letters. And these letters correspond to the different orbitals. So our s orbital, or spherical shape, that kind of makes sense. S for spherical. Makes sense. Centered around the origin of 3 axes of space, X, Y, and Z. Don't worry about which axis is labeled X, Y, or Z. You guys are used to the y-axis going vertical. You're used to the x-axis going horizontal. And the z-axis might be a new one to you that goes in and out of the page. So this one, the axes are labeled differently, but again, it's 3 dimensions of space. That's all that really matters. Now, the interesting thing about the s orbital, at energy level 1, think of it as a golf ball. If I go to energy level 2, think of it as a tennis ball surrounding the golf ball. If I go to n equals 3, now I have a softball. N equals 4, now I'm dealing with a soccer ball. N equals 5, think about it as a basketball. N equals 6, now you got a beach ball. So each orbital gets a little bit larger than the previous one before it. Questions on the s orbital? All right, our p orbitals. Why they are p? Again, it's just a funny name, but it's still just a letter. Our p orbital, there are 3 of them. Remember in the previous picture of the s orbital, there's only one, because it was a sphere and it took up 3 separate axes of space. Here, we have a singular p orbital, one on the x-axis, one on the y-axis, and one on the z-axis. So 3 individual orbitals that make up the p set of orbitals. Each set is this double-lobed type of shape that you're seeing. So the dead center, 0, 0, 0, on your axes is the nucleus, and the p orbitals stretch in 3 different directions based on x, y, and z. So again, they call them double-lobed. You could call it pedal-shaped or dumbbell-shaped, like you grab the middle and lift weights, if you will, like from a dumbbell. Could also look like a peanut, not the peanut that you're used to, maybe the one in the shell, like when you go to a baseball game and you eat peanuts in the shell. Could look like that. But again, there are 3 separate p orbitals per energy level. There is 1 singular s orbital per energy level, so to speak. We'll get to that a little bit more. Our d orbitals, these ones are, yes, they're weird. There's 5 of them. They only start at energy level 3. So energy level 1 and energy level 2, there are no d orbitals. Interestingly, in energy level 1, there are no p orbitals. So we'll get to that shortly. So the d ones look like this. Don't draw them. They kind of look like a double dumbbell or a double p orbital, or the top left one is a dumbbell and a donut, if you will. It's just, that's the shape of them. And again, these are mathematical representations of the highest probability of finding electrons. They don't actually exist. They're just showing you space where you could find an electron. F orbitals, funky shaped, if you will. F for funky. No, that's our word, funky. They're just called F. Again, craziness. Who knows where they came from? But again, they are just mathematical representations of everything. So hopefully maybe you see a little bit of a theme here on the number of orbitals. S, there was only 1. P, there were only 3. The d orbitals, were 5. And now the f orbitals, there's 7 different shapes. Let's grab our periodic table for a second. I'll hit pause. All right, we're back now. If you look at the first 2 columns of the periodic table, that is called your S block. There's only 2 columns. There's only 1 type of s orbital. If we go over to columns 13 through 18, or it could be labeled on your periodic table 3A as an apple to 8A as an apple, how many columns do you count there? Hopefully you counted 6. Now, there's 3 separate p orbitals corresponding to 6 columns of the periodic table. So let's backtrack a little quickly. 2 columns for s orbital, and there is only 1 type. Now we have 6 columns for 3 orbitals. Maybe you can see the theme forming. If we go to the D block is the center of the periodic table. It's rows 3B through 12B. B as in boy, right there in the middle, starting with scandium, SC, and ending with zinc, ZN. How many columns do you count there? Okay, should have counted 10 columns. Now, if we go back to our pictures, I'm not going to do it right at the moment, the D block, or sorry, not the D block, the D orbitals had 5 different orbitals. And here we are with 10 columns. Let's back up again. 2 columns made up the S block, columns 1 and 2, and 1 orbital S. 6 columns on the periodic table, 3 through 8 or 13 through 18, made up the P block with 3 sets of orbitals. And then the D block, middle of the periodic table, there were 10 columns and 5 sets of orbitals. Again, hopefully seeing a theme. And then our last, here we are, the F block. That's the very bottom of the periodic table, those 2 rows. We've got uranium in there, and einsteinium. If you count those number of columns, you should count 14. So what's my ratio of number of columns to number of orbitals? Hopefully you came up with a 2-to-1 ratio, 2 columns to 1 orbital. Why is this so important? Well, we'll get to it in a second, but I want you to keep that in mind for an idea of what we're getting to having to do with the number of columns and the number of orbital types of SP, D, and F. Well, different orbitals have different orientations. We've kind of discussed that a little bit. We saw that with all the pictures. Obviously, we have X, Y, and Z axis, 3 dimensions of space. So we know the p orbitals can exist on any of the axes. We saw that one. So understanding their orientation of space can also support the shape that exists, the mathematical function. Now, at the end of the day, each orbital, individual orbital, is only allowed to have 2 electrons. So if we go back to our ratio, 2 columns per 1 orbital, which basically means each column, or actually each element box on the periodic table, represents 1 electron. So the p orbitals, each individual p orbital, those lobed things, the purple ones, can have 2 electrons each. There's 3 of them. What's 3 times 2? It's 6. How many columns were in the p block? 6 columns. A coincidence? I think not. Now, the other thing about these 2 electrons that exists in each orbital maximum is one has an upspin and one has a downspin. Now, are electrons literally spinning? Not really. We have no idea. We've never ridden on an electron, so couldn't tell you. But for convention and our understanding of what's going on, and through research, of course, it's come to the conclusion of chemistry that each electron has an up or a down spin. Sometimes they call it a plus 1/2 and a minus 1/2. Just different ways to denote positive and negative, up, down, just the way it is. So hopefully we can see each orbital, maximum 2 electrons per individual orbital. But if I know how many orbitals I have, and each of them has a maximum of 2, I can then determine the total number of electrons in a set of orbitals. So 2 ways to look at it. how many electrons per individual orbital, as you see on the screen, versus how many electrons total in a set of orbitals. A set of S, a set of P, a set of D, or a set of an F. All have different numbers. But of all the orbitals, individually, they can only have 2. Questions? All right, we are stopping here. The rest of this PowerPoint or PDF that is online goes into quantum numbers. Quantum numbers are not part of the class, but if you're interested in quantum numbers, for whatever reason, please go check it out. I'm not going to get into it here today, but if you do have questions, we can discuss it individually. Thank you so much. Talk to you next time.